Swayam Prabha. Digital India. Educated India.
Hello and welcome back to another lecture on control systems. So in the previous lecture we actually started to look at this curious object called linear time varying systems, right. So they are different from what we have studied so far in the sense that they are time varying, but at the same time they have some fundamental similar properties with the systems that we have studied so far, in that they are still linear nonetheless, right. So we expect some nice properties to be carried over, while quite a few of those other properties to vanish into thin air, right. So that is probably one of the motivations behind trying to look at this, apart from the fact of course that we can sort of take a peek into this linear time varying systems using the state space method, which would otherwise not have been possible if we were dealing only with the Laplace transform and the transfer function domain methods, that is classical control methods, right. So since we can, why not just have a glimpse of what this has to offer. This is just like a sort of a digression, an excursion kind of. We are not really looking to build some solid theory of linear time varying systems in this course, right. So what we saw in the last lecture, as you can see before you in the slide, is that we defined this so called fundamental matrix, right. So the starting point when we try to look for a solution of this linear time varying system is, we say that, well, if you can cook up these n vectors of functions, right, from f1 through fn, such that each of them is a solution of the state space equation, that is x dot is equal to ax for different initial conditions at a given time instant t0, right, then you have some hope of obtaining the solution. By no means am I suggesting that it is a trivial task, yeah. You can immediately see that there is really no straightforward method, or no one is going to whisper into your ears what the solutions are going to be, right. There's that clause, that if is a big if, right. So if you can actually obtain those n so called linearly independent solutions for the state space system, then you can get any solution for any given initial condition. That is the whole crux of the matter. So let us take a closer look at this, shall we, as to what this implies. So what we saw in the other day was that, well, if you have this f, which we are calling as a fundamental matrix, whose columns are basically these functions, sorry, that is not at t2, it is at t, it is f2, f3 of t, so on till you go on till fn of t, yeah, and remember that each of these is an n tuple. So this is a vector, right. So we say that this f dot of t is equal to a f1 t, yeah, because remember now we are equating column wise on both sides. So if f1, f2, f3 till all of them till fn are indeed the solutions of the state space equation, then they must satisfy this. So therefore we say that this is a times f1t dot 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 till fnt, which is nothing but a ft, right. And then we say that, well, so therefore if you have the fundamental matrix, in fact the fundamental matrix is a solution of the matrix differential equation given by a m is equal to, or rather I should write m dot on the left hand side, yeah. So you have, let me not skip the arguments here, because they are all time varying now, yeah. So let me just skip the argument here. So this is the matrix m dot When I say m dot, I mean entry wise, each entry of that matrix. So this is, remember, an n cross n matrix, yeah. M dot is equal to AT times MT, yeah, where of course MT naught is equal to FT naught, yeah. So FT, let me put a different color on that. So this thing I have put a brace under, a blue brace under, yeah. So FT happens to satisfy this matrix differential equation, okay. Now you notice that what we sort of derived in the previous lecture was that if this matrix FT has to contain linearly independent solutions, yeah, of the system that is given by xt dot is equal to AT xt, yeah. Each column of F, the fundamental matrix, contains a solution of this equation originally, right, and we are also claiming that this F is invertible or non-singular, then it better be non-singular for every instant of time t, yeah, because we showed you that if it is not, if it manages to be singular for one instant of time, then it is going to be singular for every instant of time. So the converse is that if you have to have non-singularity of this Ft, then it cannot afford to even be singular for one particular value of t. The property we used there, without proving of course, was the uniqueness of the solution, right. As I said the other day as well, that is well beyond the scope of this course, the proof of uniqueness of the solution. So we will just assume that the solution is unique, and once you assume that, then it is straightforward to see that if the solution is unique, if you can manage to find one solution, then that will be the only solution. And we saw that if F manages to be singular for a particular instant of time t, yeah, then it will be singular for every instant of time t. So therefore conversely, if F is non-singular, then it is non-singular for every instant of time t, right. So therefore at t is equal to t0 also, yeah, remember this is a constant matrix. Now Ft naught is a constant matrix, and what sort of a constant matrix is this? It is an n cross n constant matrix, yeah. So n cross n constant matrix which is non-singular, which means it is full rank, yeah. If it is full rank, then what else do we know about it? Its columns and rows are going to be linearly independent, but here we do not bother about the rows, so we say that its columns are linearly independent. So Ft0 is non-singular, which is implies and implied by that columns of Ft0 are linearly independent. And if you know a bit of linear algebra, if you have done some preliminary courses, you would know that in an n dimensional space, if you have a bunch of n linearly independent vectors, then they form a basis for that vector space, right. In other words, that just means that if I write these columns F1 t naught, F2 t naught, yeah, I am saying that of course they have to be linearly independent, because otherwise this F fundamental matrix will have to be singular for every time instant t. That is what we proved the other day. So therefore this set is a linearly independent set having n elements, right, and they belong to Rn, yeah. They means these elements yeah belong to Rn. So therefore they form a basis. In other words, that basically means that every vector in Rn, that is every n tuple, can be uniquely, so this is a bit of linear algebra, I mean please revisit some fundamental ideas, concepts from linear algebra, and you would immediately recall that if something form, if you have a basis set, it means that every vector in the vector space can be represented as a unique linear combination of the basis set, represented as a linear combination of this basis, right. So therefore, if I give you any, that is any x t naught is equal to x 0 can be written as x naught. So remember, these are also n tuples, yeah, and as I said, these are all constants now because I fixed up the time instant t 0, yeah. So it is not a function of time anymore, these are just some real numbers, right, not even functions of time. So then I can write this as C1 f1 t 0 plus C2 f2 t 0 plus dot 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 till I go till Cn fn t 0, right, which is nothing but, if you think a bit carefully, you will see that this is nothing but f t 0 times the vector C1 C2 dot 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 till Cn. In short, let me call this vector, so this is another n tuple, this Cn, C1 through Cn, yeah. In short, I can just say that is f t naught times C, where this C is basically an n tuple. So that means any initial condition you give me for which you want the solution of this differential equation, that is this linear time varying differential equation, yeah, then I can cook up the C vector and tell you that, okay, so you have given me an initial condition, a set of initial conditions like S x naught, yeah, which is of course also r to the n, yeah, and I can tell you this C1 C2 C3 till Cn, yeah. So that means every linear combination, every initial condition can be written as a linear combination of the columns of the fundamental matrix at t is equal to t 0, okay. Now, having obtained or having come this far, what can we then say? Now notice, I would like you to cast your attention back to the slide that we had the previous day, yeah. So what does this say? We know that f dot is equal to at ft, yeah, and now we have this x naught is written as ft naught times some vector c, right. So therefore, from this, can I not write that the c is ft naught inverse times x naught? Of course I can, because I know that this ft is invertible for every time t. If it were not, then it would be non-invertible for every time t. That is what we proved the other day, that is the beauty of that result, right. So then I can write the c in this fashion, yeah. But why am I interested in writing the c in this fashion, yeah? Why exactly do I want to write the c in this fashion, yeah? Because remember, I have f t dot is equal to a t times f t, yeah. This is true, is it not? Yeah. Now I am trying to basically find a solution for the equation x t dot is equal to, so this is, we want to solve for the homogeneous equation, that is no forcing function, x dot is equal to a t x t such that x t naught is equal to x 0, right. So this is what we are looking to solve, okay. And now I know that this x 0 is nothing but, I can always cook up some c vector such that it is given like this, yeah. So this I already know that this I can already obtain in terms of the f. So what I want is this x t, what is it going to be, yeah, that is the question. So how can I put all the pieces in the puzzle together here, yeah, that is going to be my the crux of the whole matter, okay. So just think for a while, just think for a while that if you take say C F1, so consider C F1t, sorry C1 F1t plus C2 F2t plus dot 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 till Cn Fnt, then take its time derivative, So let us say this is something that I have cooked up, this C1, the same C1s by the way which describe my initial condition, okay. Then what do I get? I get C1 F1 dot, so I am now omitting the T, plus C2 F2 dot plus dot 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 till Cn Fn dot, But what is that in turn? Now notice that that is going to be nothing but C1 At F1t plus C2 At F2t plus dot dot dot, likewise you go till Cn At Fnt, So that is going to be nothing but At times Ft times C, okay, should not write the implies, it is basically equal to, so this is equal to nothing but this, okay. So I first started with this whole thing that I am putting in the green box now as a trial. You remember early on when you did not know these different methods of solving a differential equation, we just tried some solution, we wanted to try out if that solution works. So here we are trying to do exactly that, right. So we will check whether this works for us. Now what is this? Remember that this is nothing but Ft times C is equal to this, So what we found now is that this Ft times C satisfies xt dot is equal to At xt and also satisfies, by the way we have chosen this C, you see, by the way manner in which we have chosen this C, it also satisfies the fact that f t naught C is equal to x naught, So therefore this is my candidate for a solution, and again I am going to invoke that property of uniqueness. So if I found one solution, then that is got to be the only solution, again something I am stating without proof. So therefore I tried with a trial solution. What I did was, you give me an initial condition, suppose somehow someone else has given me these set of n linearly independent functions, each of which, these functions, by functions I mean n tuple of functions, okay. So there is basically f1 which is an n tuple of functions, f2 which is an n tuple of functions, so someone has given me this fundamental matrix, okay, and then you give me some initial condition. Then the trick to finding the solution, it turns out, is I try to find out what sort of a linear combination of the columns of the fundamental matrix at t is equal to t0 is this initial condition that you have given me, Once I am able to evaluate that, I can evaluate that by using this, because ft0 is invertible, in fact ft is invertible for every t as we proved the other day, so therefore I can always obtain this C, right. So now once I have obtained this C, what I need to just do is, I need to just say that, well, ft times C, ft is this fundamental matrix which somebody has already given me, C is something that I have obtained based on the initial condition that you have given me, okay. And now I am claiming that ft times C is a solution of this homogeneous linear time varying equation, and I have just shown you that it indeed satisfies the initial condition as well as the dynamics, therefore it must be a solution. And now again, by some bench pressing sort of thing that I am doing here, which is to say that I am not proving it, but I am just claiming that you have to take my word for it, that, well, this actually has a unique solution. So therefore, if you find one solution, that is got to be the only solution. So since I found that one solution, this is the solution. So therefore, the solution is xt, let me put that inside a green box, xt is equal to ftc. But you might not be very happy with the C. After all, the C is something that I have obtained. This doesn't give me something methodical. After all, the thing I started with is F, the fundamental matrix, yeah. And so someone's given me the fundamental matrix, someone's given me the x naught. So I want the solution in terms of those fellows only. But the C is something that I derived along the way. So how do I replace this C? Already it's there before you, right? So I'm going to just replace this, substitute C here, and then the final solution is going to be xt is equal to ft times ft naught inverse times x naught. And now you see I have got the entire solution. You give me any initial condition, someone's given me the fundamental matrix, which is basically a set of n tuple of functions, yeah, such that each column of the fundamental matrix is a solution of the state equation, and those functions are linearly independent, those n tuples are linearly independent. So someone's given me the fundamental matrix, someone's given me the initial condition, and then I can tell them that, well, you need look no further, this is going to be the solution. Now it turns out that for this you just need knowledge of the fundamental matrix, that's it, just substitute t1s and substitute t01s, t0 is a constant, yeah, the same initial instant from which you are starting your ODE or sort of setting it up, yeah, your observation starts at t0, so it's the initial value problem. Now I'll define another term here, this it turns out is defined as the state transition matrix, okay. So far I have just been talking about this fundamental matrix, now this is called the state transition matrix. So what is the state transition matrix? It is defined in this fashion. If you know what a fundamental matrix is, then the state transition matrix phi of t comma t naught is given by ft, so this is the definition, ft times ft naught inverse, alright. So this is what it is, alright. So why is this t comma t naught? Because it is time varying, you see. So as I showed you the other day, if it is time invariant, then the only thing that matters is the duration of time that has elapsed since you started your observation and the current instant, yeah. So whether you start your observation in 2021, yeah, and you look 1 year hence, whatever solution you will get, if it is a time invariant system, then if you if you had set up your equation in 2015 and if you had looked 1 year hence in 2016, you would have got exactly the same solution if it is linear time invariant. But for linear time varying system, the system has changed, the parameters have changed with time. So whatever output you got 1 year later by setting it up in 2016 or 15 would not be the same as what you would get by setting it up in 2021 and looking for the solution in 2022. That is the case of time varying system, right. So therefore you cannot just define this as a function of t minus t naught, but it is basically dependent on when you are looking for the solution and when you started your observation, both these instances, not just their difference, yeah, very important. So this is how we define the state transition matrix, and now at this point you should be able to recall something very similar that you have done, in fact we have been doing just a couple of lectures back, yeah. It turns out that this has an uncanny resemblance with something we already know, the matrix exponential, remember, in case of the linear time invariant system. It turns out that the matrix exponential is nothing but the same state transition matrix for a linear time invariant system. So immediately there are a few properties of this state transition matrix, yeah. So some quick properties, they are not really very difficult once you know how you have obtained this state transition matrix from this fundamental matrix, yeah. Once that concept is clear, you would know that it is obvious. The first property is that phi t comma t naught is non-singular for every t. Yeah, why should it be so? Well, of course, just see what is the definition here. So, check that f t naught f t inverse is an inverse for phi t comma t naught for all t. Yeah, just try it out, just hit this fellow either on the right or on the left with this fellow, and you see you will end up with identity, right. So, if at every value of t there is an inverse for this fellow, this state transition matrix, then obviously it is going to be non-singular, right. That is the definition of non-singularity. And why am I sure that this ft inverse will exist? Again, go back to the definition of fundamental matrix, the property we proved for the fundamental matrix, the fact that the fundamental matrix must be non-singular for every time instant t. That is its very definition, its property, okay. Right. So, this is a very trivial property then. Once you know that it comes from the fundamental matrix, there is really nothing to prove here. The second property is that phi satisfies this, excuse me. So, phi satisfies this phi t t naught. If you take the partial derivative with respect to time, it satisfies the matrix differential equation t comma t naught with initial condition phi t0 comma t0 is equal to I. Yeah. So, that same equation you see what we started with earlier when we were dealing with the fundamental matrix. Yeah, when we talked about it in terms of the fundamental matrix, then the initial condition of this matrix differential equation was f t naught. Now, I am saying if you want the initial condition to be the identity, then your fundamental matrix. So, basically it is like if you know of any iterative method. So, that is why I said, it is not a trivial problem. This analysis, all this we are doing is fine, but computation wise it is a very difficult problem to obtain the state transition matrix. By no means is it trivial. So, if you know of any analytical method or any computational method, rather not analytical, if you know of any computational method by which you can iteratively sort of keep integrating, Euler integration or whatever, then you better start, you set up your matrix differential equation with an initial condition equal to the identity and you keep integrating it. Yeah, and what you will get at the output of the integral is basically going to be this state transition matrix, right. Not a very wieldy way, is it? I mean, it is rather unwieldy, right. So, yeah, that has been a long standing problem, how to actually get efficient, computationally efficient methods for getting this state transition matrix. It is not like evaluating the e to the at, for which we have seen already 3 methods, right. So, of course, that is again not to say that computationally that is an easy thing to compute e to the at. We are talking about hand computation for the purpose maybe for your examination or for your concepts, right. So, there we mostly do not go beyond 3 by 3 matrices. For large matrices, even the a to the e to the at, that is the state transition matrix for a linear time invariant system, evaluating that is also not a very easy task, okay, right. So, we see that this is the second property. What is the third property of this? A third property is very interesting. You see, we can say now that phi t comma t1 is equal to phi t comma t2 and then phi t2 comma t1. Again, you take this as an exercise, just plug in these suitable values from this expression here, the fundamental matrix. You see, this is going to be ft f inverse of t2, and this is going to be f t2 and then f inverse of t1. So, then you will get this as f t1 inverse. But why is this important? Why is this so interesting? It is interesting for the simple reason that, now notice that for x dot t is equal to at xt with xt naught is equal to x naught, we have xt, earlier we described the solution in terms of the fundamental matrix, now we will describe the solution in terms of the state transition matrix, and that is what justifies this name. You see, what is this showing me? That this transition matrix is like, if you give it as input, it is like an operator to which if you give the input, the state vector at some time instant t naught, then the output of that operator will be the state vector at the time instant t, right. That is what, that is why so it is as if it is telling you how the state transitions as time evolves, how the state transitions from one particular bunch of values to another bunch of values, yeah, to what bunch of values does it transition as time goes on, yeah. So without even looking at the differential equation now, without solving for this, once you know the pattern of this, if you can, that is, of course, if you can find some pattern of this phi t comma t0, the state transition matrix, then this actually tells you how your state transitions. So the name is very common sense based, right, that is why it is called a state transition matrix. So now notice, in the light of this, what does this tell you? It tells you that if I have 3 instants of time, say t1, t2, t3, right. So if I know that this is my vector, state vector at t1, this is my state vector at this is at t1, this is at t2, and this is my state vector at t3, right. Then what can I say? I am saying that, well, for this bit the transition matrix is phi t2 comma t1, for this bit the transition matrix is phi t3 comma t2, yeah. So it turns out that if you know piecewise in these small segments the transition matrix, then you actually, if you want to, this is like composition of operators, yeah. So if you want to find out the overall transition matrix from t1 to t3, all that you need to do is you just need to multiply those two matrices, yeah, t3 t2 times phi t2 t1, yeah, that is going to be equal to phi. So everything, this entire transition from t1 to t3 is captured by these piecewise transitions from t1 to t2 and t2 to t3, yeah. So that is what this property is telling us, okay. So that is why this is an interesting and important property. So yeah, we just, now you see that you can immediately relate to this state transition matrix in exactly the same way as you did with the matrix exponential for the linear time invariant system. So having come this far, it would be rather sad if we did not go a little further and sort of try to draw the analogy and completely close the case thereafter, right. So what are we trying to do here? We are trying to draw some analogy, we are trying to draw some parallels between the linear time invariant case and the linear time varying case that we are now seeing, right. So here is the first sort of claim which is a little non-trivial. So the claim is, not that I am suggesting that this particular result that I am claiming here is going to help you computationally in obtaining the state transition matrix, but here is the claim. The claim is that this phi t t naught is given by this series, yeah, this is called the Newman series. I do not remember if it was a double n or a single n, excuse me for that, yeah. So then this is given by this t naught to t a tau 1 d tau 1 plus t naught to t and then another integral from say t naught to tau 1 a tau 1 a tau 2 d tau 2, sorry, not the bracket here, there should not be a bracket here, d tau 2 d tau 1 plus I will drop to the third term because this is an infinite series, just like you had an infinite series for the linear time invariant case, here also you will have an infinite series, yeah, and then you have an integral from t0 to tau 1 and then you have an integral from t0 to tau 2, yeah, and here you will start integrations from let us say d tau 3, d tau 2, d tau 1 and in the middle in the integrand you will have a tau 2, sorry, a tau 1, a tau 2, a tau 3, okay. Excuse that pathetic handwriting over there, it's just a tau 1, a as a function of tau 1, a as a function of tau 2, a as a function of tau 3, and so on. So it's an infinite series, so it goes on till infinity, ad infinitum. Now the claim is that this is nothing but phi of t comma t naught, the state transition matrix. So what is the way to show this? What is the most quintessential property of this this state transition matrix? I know that this state transition matrix, for one, it better satisfy that phi t naught comma t naught is equal to identity, yeah. So if I check that these two properties are satisfied, because remember every other property you can prove from this, right. So if I prove that these two properties are satisfied, the second property is that if I take the partial derivative of phi t comma t naught with respect to t, then I should get, yeah, I should get this, because this is after all the solution of the matrix differential equation. So taken together these two conditions are just telling me that phi is the unique solution of the matrix differential equation given by m dot is equal to am at mt, yeah, where the initial value of this m is going to be the identity matrix. So if I can prove these two, then I would be done showing that. So if I, essentially what I am saying is that if I can show that the right hand side satisfies these two properties, then I am done. Now you see there is nothing to prove in the first one, you just plug in, instead of t you just plug in t0. What happens? If you plug in t is equal to t0 here, this integrand vanishes. If you plug in t is equal to t0 here, this integrand also vanishes. So every integrand you see, because the last integral is from t0 to t, so you just substitute t0 instead of t, because after all that is what you are doing here, no, in this first property, you are substituting, replacing t with t0. So you substitute t with t0 in every one of these integrations, all these integrations will vanish and you will just have identity. So this property is proved, yeah, just write it up a bit, it is nothing, not a big deal at all. So this property is proved. So what we need to essentially prove, the non-trivial property, is that we have to show that this series, this Newman series that we have now written down, it should also satisfy this matrix differential equation, yeah, this differential. So we have to differentiate this on both sides. Now while differentiating this, I urge you to recall, you must have done this at some point in time, maybe during your first or second year of undergrad mathematics curriculum, this thing called differentiation under the integral sign. So basically the integral is happening with respect to some variable, but you are differentiating with respect to some other variable. So there is this property, if you do not recall, if you do recall it is well and good, if you do not recall, let me just refresh your memory a bit. So there is this property, this so called Leibniz rule for this differentiation under the integral sign. What does this Leibniz rule say? It says that if you have psi, a function of time, given by let us say, what should I call it, I should not use f and g, okay, ht gt, so the limits could also be functions of t, yeah. The integrand is some gamma which is some function of t as well as tau, but it is being integrated with respect to tau, okay. Then the rule says that if you take the derivative of psi with respect to t, then on the right hand side what you have to do is, first you differentiate the upper limit, provided it is differentiable of course, so we are going to assume that it is differentiable. So you take g dot t, and in this integrand you just replace the t with gt, because after all this gt was supposed to be the, sorry, the tau with gt, I am sorry, excuse me, I am getting carried away. So this tau was, after all the tau was supposed to go run from ht to gt, right. So you better replace this with gt here, yeah, minus now the derivative of the lower limit, which is ht, times gamma t comma ht, yeah, plus now you retain the integral as it is, ht gt, and inside the integral you differentiate gamma with respect to t, not tau, okay, and then take its integral. Yeah. So this is basically the Leibniz rule, in case you have forgotten. Yeah. So this is what Leibniz rule is. Now if I want to apply this Leibniz rule to each of these integrations here, you see what is the function of t here? There is only one thing that is a function of t. You see the way in which I have written the series, only the upper limit, that too of the last integration in each of these, is a function of t, because everything else is integrand. Look at this integrand here, there is no question of any t here, right, there is no, it is not a function of t. So this last term will not arise. The lower limit is, none of the lower limits of the integrands in fact are actually functions of t, they are all constants, right. So they will also not matter. So the only term that I will have to deal with in my particular example is just this, right. So if I just apply this property, then what do I get? Let me look at the first term here. So if I just for example take the first term here, so excuse me, so of course the identity will vanish, so I am not talking about the identity. This is of course a constant, so you differentiate with respect to time, it vanishes. What about the first term here? What I will get is basically a of t, that is it. So basically the first term is going to be a of t. Why? Because remember I am going to replace the tau with gt. So what is my tau here? Tau is tau 1 and gt is just t, so it is going to be at. Yeah, and g dot of t, what is g dot, what is ddt of t? That is 1. So it is going to be basically this, to be precise it is going to be 1 times this t. What about the second term? You see they are all going to shed one integration each. Yeah, they are all going to shed one integration each, right. So what is going to be the second term here? Look at the second term. Again, up until this part nothing matters. Sorry, not that, I should probably exclude that d tau 1. Yeah. So up until this part nothing matters. Similarly here, up until this part nothing matters. This is my gamma, the way I have defined the gamma here, this is the gamma, alright. So nothing matters. So the only thing I have to differentiate is this t, and the ddt of t is 1. So in each of these fellows then I will have plus 1 times, what am I going to pull out of this? Well, I am just going to pull out this excuse me, whatever is sitting here as the last integral, that is basically this, right. So this is the term here, just like this is the term here, because this is going to be integrated with respect to tau 1, with tau 1 running from t0 to t. So I am just going to pull out this, yeah. So this tau 1 is my proxy for tau here, right, this is my tau. So the last integration, the nested integrals inside, they do not matter, it is just the last integration that is going to matter, yeah, because I am just taking the derivative with respect to this one. The others, their limits are not functions of time, yeah, and the integrand itself is also not a function of time. So as I said, I do not need to bother about this term or this term, I am just concerned about this term and that too of the first integration, okay. Now if I do that, then each of the terms you see I am going to just pull out another at here, but with this comes, now in the second term only one of the integrations will remain. So it is going to be this a tau 2 d tau 2 0 to, okay. So remember that I have to substitute this thing here, this h of this g of t as the upper limit. So g of t is t, right. So wherever there is this tau I have to substitute t here, yeah. So what is my tau? The role of tau is being played by tau 1 in my case, right. So that is another subtle thing. So this tau 1 is basically playing the proxy of the tau that I have defined in my general definition of the Leibniz rule here, right. Yeah, this gt, yeah. So now my, instead of d tau here I have d tau 1 here. So wherever you see tau 1, it will play the role of this tau. So you replace the tau with gt. So wherever you see tau 1, you now replace it with gt. What is gt? Gt is t, right. So you replace it with t, right. So now notice what is this? This is basically now the original expression's first term. So it turns out if you carry on like this, yeah, you can pull out this, not an implies by, you can basically pull out this AT outside, and what you are going to get inside is I plus, this integration 0 to t a tau 2 d tau 2, this is just a running variable, whether you call it tau 1, tau 2, gamma, alpha, beta, nothing, it does not matter, yeah. So it is basically this, but this I have already given it a name, it is called a placeholder, right. So then this is going to be nothing but AT times phi of t comma t naught. So if indeed I had started with defining my phi of t comma t naught like this, then I see that it actually satisfies this equation, yeah. So therefore this series indeed, I am not saying is very useful computationally, yeah, but this series in theory gives you the state transition matrix. And now look at something curious, if you now want to sort of retrace your steps back, that is if you are not very happy with, I mean of course there are still issues with this, I have not proved a lot of things, I have just imposed it upon you again, but this is another way to see. Now you go back to the time invariant case. So in the time invariant case, this A will not be a function of time, yeah. So if this A is not a function of time, then what is this going to be? This is all going to be just A, right. So what is this in the time invariant case? In the LTI case, what do we have here then? Phi of t comma t naught is given by I plus, look at this series, yeah, this is going to be AT, yeah, the A is a constant, so it is going to be pulled out, so it is going to be AT, yeah, AT minus t naught to be precise, plus, now you look at the second term here, sorry here, so it is going to be A squared, yeah, so you first integrate and you get t, and then you get integrate another time and you get t squared by factorial 2, rather t squared by 2, yeah, so you get A t minus t0, so A t minus t0 squared by factorial 2, likewise. But what is this series? This we have already defined by our definition, this is e to the A t minus t0, right. So in other words what I am saying is that this, we have made so much effort to sort of derive the state transition matrix, but it is exactly as we suspected, yeah, this is playing the same role as the matrix exponential as can now be seen, because just like here this in the linear time varying case, this when multiplying xt naught gives me xt, here also I have e to the A t minus t naught when multiplying xt naught gives me xt, yeah. So this is indeed this matrix exponential. Now you learnt of another name that this has, this is also the state transition matrix for the linear time invariant state space system of equations, right. So that is the analogy. So hopefully you have enjoyed this part, seeing it from another aspect and seeing what the commonalities between the linear time invariant and the linear time varying cases are, and also how the linear time varying case is actually way more complicated, yeah, because there are a lot of things we have supposed that someone has told me what the fundamental matrix is, right. That is a huge piece of information. It is by no means a trivial problem, it is way more complicated in fact than just obtaining the n eigenvalues, yeah. You might still have some hope for using numerical methods to find eigenvalues, right, but obtaining this n linearly independent solutions which is required for the linear time varying case is really not at all trivial by any means, okay. So before we close out this bit of discussions on this linear time varying case, here is a warning. So we made a big deal about this poles and poles of transfer functions and their relations with eigenvalues of the A matrix in case of this time invariant system, right. So you might wonder, does the eigenvalue of, or does any eigenvalue of this AT, right. So the question is, do eigenvalues of AT have any special role to play in obtaining the solution like they did in case of LTI systems. So, remember in the LTI systems we had this eigenvalue eigenvector equation, and therefrom we got these sufficient number of eigenvectors, if not then some generalized eigenvectors. If there were complex eigenvalues, then we took this real part and imaginary part, isolated them together, and then eventually cooked up this bunch of n linearly independent eigen or generalized eigenvectors, and then we got it to a diagonal form or Jordan form or block diagonal form, whichever is more convenient, which allowed us in turn to evaluate this e to the at, the matrix exponential, right. So, that is indeed pivotal to obtaining the solution of a linear time invariant system. Now, you might wonder if something like that also happens in case of linear time varying systems. For one, you can have no such hope, because now in general it is not even guaranteed that these eigenvalues will be constants. Yeah, if the A matrix has its entries which are functions of time, then if you just try to apply the determinant of Si minus At or lambda minus At, so if you just try to find out determinant of lambda I minus A of t and equate it to 0, then your lambdas will probably be functions of time. Let me not use f, let me use some lambda 1 t, lambda 2 t, so on and so forth, right. So, some such functions of time you might get, yeah. So, this is really not very helpful at all, it seems, right. The other thing, the other very crucially important thing, let me give you an example, and you can actually do this computation on your own to convince yourself that what I am saying is indeed correct, yeah. So, suppose I give you this matrix, let me have it. So, I have, yeah, cos squared t 1 minus 1.5 cos t sin t minus 1 minus 1.5 sin t cos t minus 1 plus 1.5 sin squared t, okay. Now, listen, this is clearly a time varying matrix. However, by some apparent accident or good fortune apparently, we will see later on it is really not much of a good fortune after all, but by some good fortune we find out that even though each entry of this matrix is a function of time, the eigenvalues actually turn out to be minus 1 plus minus square root of 7 upon 4, yeah. So, you might now raise your hopes high. Well, okay, you said that if you find eigenvalues that are functions of time, then it seems like there is a glitch, so it does not help. But I wonder if the eigenvalues do not end up as functions of time, but rather as constants, can this somehow help? Well, unfortunately I will have to bring you the bad news here, this really does not help at all, okay. So, do not go into the pitfall of thinking like whatever is the eigenvalue, whatever story the eigenvalues told in case of the linear time invariant system, we can extract some such similar story from the eigenvalues of the A matrix in case of a linear time varying system, okay. The eigenvalue evaluation will be an exercise in futility if you are really trying to analyze anything qualitatively about the system when the system is a linear time varying system, yeah. Which brings us to our next most important topic, about which we will launch into much greater detail during the next lecture, but let me just introduce this to you. You might have already guessed that one of the most important properties, yeah, of a system is this so called stability, yeah. In the transfer function domain we have seen that it is basically the poles of the transfer function that determine whether a system is stable or not, yeah. And we have already said that, well, if you want your system to be stable, your poles better be on the open left half plane. In fact, we have also employed this Routh-Hurwitz criteria, one of the earlier methods, to check whether a given polynomial has all its roots on the open left half plane or not, right. So, that is a very important method. Now, it turns out that that sort of a stability notion, yeah, is really what do we call an external stability, yeah. There is a name for it which you might have encountered in some other courses on signals and systems, yeah. So it is called Bibo stability, which is basically bounded input, bounded output stability. That means if you give a bounded input to a system, yeah, that means this input is bounded in magnitude, then the output also, so it is bounded in magnitude for all instants of time, then the output will also be bounded for all instants of time. And it turns out that the condition that you require for that is exactly the requirement that the poles of the transfer function better be on the left half plane, because by the classical definition of Bibo stability it is not very helpful. So we will get into the classical definition and we will do a little bit of working out of that condition, yeah, but we will see that the classical definition per se does not help. The more useful check or test for Bibo stability is, given a transfer function, find out where its poles are, yeah, as we already did using Routh criteria, and figure out if those poles are all in the open left half plane. If they are, then it is Bibo stable. Now you might have already seen, right when we started this state space based discussions, we encountered this example, right, where we had this two blocks that we put in together, s minus 1 upon s plus 1, and then we had this 1 upon s minus 1, right. So you can take the combination of these two and you can take the overall transfer function to be nothing but 1 by s plus 1, right, and we saw that we run into problems because we did not account for the initial conditions. What are the initial conditions? They are basically some states. So of course the transfer function method by in and of itself does not account for the initial conditions. The transfer function by definition is obtained by setting the initial conditions to 0. So that is why if you are using just the transfer function based methods, it does not give you sufficient internal description, right. It turns out that for internal stability, which we will also call asymptotic stability, yeah, none of these terms we have defined so far. We will get into those definitions in the next class. I am just giving you a brief idea into what we are going to do in the next lecture, right. So it is going to be all about stability in the state space domain. So this internal stability or the asymptotic stability does not really look just at the poles of the corresponding transfer function. So you are given basically say A, B, C, D now, yeah. When you are dealing with external stability you would be given a GS, but now you are given an A, B, C, D. So if you think that okay, I am just going to find out the C Si minus A inverse B plus D. So this is going to be my GS, and then I better apply the same tools as here, right. But then that way you are only going to get as far as the Bibo stability, yeah, because then if you convert the state space system to its corresponding transfer function and check for the same rules for stability like here, then you would actually have no insight about what is going on inside the system, right. So in order to do that, it turns out what we need to do is to look for the eigenvalues of A, okay. So we are again back in the domain of linear time invariant system. Our brief foray into linear time varying systems is over. So we are back to talking about linear time invariant systems. So these eigenvalues of A crucially determine whether a system is asymptotically or internally stable or not. Once again, to sort of take a quick recap of what we did in this case, the last thing we did here, you see here also you might sometimes by accident get eigenvalues in the linear time varying case that are basically not functions of time, but that tells you nothing whatsoever about stability. Do not, I repeat, do not get into the pitfall of assuming that it is going to be stable just because the eigenvalues happen to be independent of time, okay. There are totally different classes of rules or techniques for determining the stability of linear time varying systems. We are not really going to get into that, okay. There are Lyapunov based methods, yeah, for that. So if you go for courses on nonlinear controls later on at an advanced level, you would learn about these, okay. We will not get into that in this course, okay. The key is the moment you get into linear time varying systems, they are a completely different beast altogether. All these things that hold for linear time invariant systems, these intuitions that we have for these eigenvalues and so on and so forth, yeah, none of this works there, okay. So hopefully that is something lesson that you have taken to heart, and you will not make that mistake of encountering a linear time varying system if you do, and then thinking that it is just a small bit of tweaking of the linear time invariant case and we will be able to solve it. No, it is a completely different ball game altogether. Okay. So in the next lecture we shall dive deeper into this notion of stability. We shall take a closer look at Bibo stability and asymptotic stability and see that asymptotic stability implies Bibo stability, but the reverse, the converse is not necessarily true. Okay. So until then, take very good care. Thank you.